Alright guys, welcome back to Underground Science, and in this video, we'll be picking up from where we left off in the part 1 of our Proximal Convoluted Tubule video, alright? So make sure to go check that video out. So we left off by saying that we actually end up reabsorbing around 100% of our glucose and amino acids in our Proximal Convoluted Tubule. Alright, so we actually end up reabsorbing around 100% of our glucose and amino acids in our proximal convoluted tubule, right? So let's go and draw an arrow into our blood. All right, but we never talked about how amino acids are reabsorbed. So let's go and look at that, all right? So let's go and pretty much just draw the same thing, right? Let's go and draw a blood vessel here. Okay, so this is our blood vessel, a pretty horrible looking blood vessel. So let me try to make it at least a little bit like a kind of like a cylinder shape, all right? And then, so it's going to be our blood, right? And then we just have to draw our proximal convoluted tubule cell. All right, so it's going to be our proximal convoluted tubule cell. All right, so it's going to label that. And then we can draw our lumen of our proximal convoluted tubule in our nephron. Okay, so it's going to be our lumen of our proximal convoluted tubule. So we went over the reabsorption of glucose through sodium, right, and also some water. And so let's go ahead and look at the reabsorption of amino acids. So again, it turns out that we have a sodium amino acid transporter here. So this is going to be our sodium amino acid transporter. All right, so let's look at this. It's going to be our sodium amino acid transporter. All right, sorry about that amino acid word. It looks like it's one word, but it's not. All right. And so what this transport is going to do is what it says, right? So sodium, again, is going to be inside our lumen, right, in high concentration. And sodium is going to go from high to low concentration. And what it's going to do is because sodium goes from high to low concentration, it's going to help take amino acids from low to high concentration. So again, we see secondary active transport. So then amino acids, right, are going to go from low to high concentration. All right, so then we're going to have some amino acids, sorry, that's random dot, go here. So this is going to be our amino acids. So again, we're going to have low concentration of sodium, all right, just like we discussed here, low concentration of sodium, all right, and then we're going to have high concentration of amino acids. All right, so amino acids have to move from low to high concentration, but we have sodium here to help because sodium is moving down its concentration gradient. So this is a secondary active transport, all right? It's not using ATP directly, okay? So that's that. And then once we have our amino acids in, we have a channel on the basolateral side, right? We have a channel on the basolateral side. So let's go and draw that real quick. And you know what, just to do it again, even though we already labeled it here, let's go and label it again. So this is going to be our basolateral side because it's the side where our blood vessel is, basolateral side, and right here is going to be our apical side, so our apical or apical side, all right, because that's the side nearest to our lumen, okay? So it's going to be our apical side, and this is going to be our basolateral side. All right, on our basolateral side, we're going to have a channel for amino acids to enter the blood. So amino acids are then going to go through this channel and enter the blood. All right, and again, right here, as we mentioned it, almost 100% of amino acids are going to be reabsorbed in the proximal convoluted tubule. All right, so 100% of these amino acids will be reabsorbed in the proximal convoluted tubule. All right, so our amino acids have reached the blood, right? But remember, if we keep on doing this, right, sodium concentration is going to build up inside the cell. But remember, sodium was going from high to low, and that's what was helping the amino acids get into the cell too. So we don't want sodium to go high here, or else sodium won't be able to get inside, right, without the use of ATP. And we don't want to use ATP here. This is secondary active transport, right? So we need somehow for the concentration of sodium to stay low. So the way we do that is we have, again, sodium-potassium transporters, sodium-potassium ATPase transporters. So we're going to have a sodium-potassium ATPase transporter. Let's go and draw 2 here, but let's go and label this one right here. All right, so we're going to have 3 sodium molecules, right, going out into the blood, 3 sodium, and then we're going to have 2 potassium molecules, right? So we're going to have 2 potassium molecules going from low concentration to high concentration. All right. So we have, again, we have sodium going from low to high concentration. Then we have potassium going from low to high concentration. What does that mean? That means we need energy, right? We need ATP for these sodium potassium ATPase transporters. All right, remember this ATP will actually break down into ADP plus an inorganic phosphate. All right, and so that's pretty much how amino acids get reabsorbed into the blood. All right, so that's how amino acids get reabsorbed into the blood via our proximal convoluted tubule section in our nephron. So another thing we can talk about is how our proximal convoluted tubule actually can regulate pH. All right, through the use of our carbonic anhydrase, right? Carbonic acid, bicarb, hydrogen cation, CO2, and all that. All right. So let's go and see that in another page. So we have our blood again, our blood peritubular capillary, right? That's like so. And so let's go and label this as our blood. And then we have our proximal convoluted tubule cell here. So proximal convoluted tubule cell. And then we have our lumen of our proximal convoluted tubule. All right. And so we have a transporter here on the apical side of our proximal convoluted tubule cell that's responsible for bringing sodium in, right, from high to low concentration. So sodium, let's go and write this in a different color. All right, so sodium will actually go, so let's go ahead and make this full orange. Sodium will go from high to low concentration, and these hydrogen cations will go from low to high concentration. All right, so it's secondary active transport here. Okay, guys, so, and then now what's going to happen is that we actually have a good amount of water inside our proximal convoluted tubule cells, right? So let's say if we drew some water here, or just one for now, what can happen is from the blood, we can have CO2, carbon dioxide gas that can enter our proximal convoluted tubule cell. So if we drew CO2 here, entering our cell, right? Remember from our intracellular erythrocyte videos, we know these reactions that occur between water, CO2, and all this acidity, right? Or not all this acidity, but all these acid and carbonic acid, right? Carbonic anhydrase and all that stuff. So we know that pretty well. So what can happen if we have water and carbon dioxide, right? So once carbon dioxide enters, we actually have carbonic anhydrase present, right, inside our cell that will help convert the reaction of H2O plus CO2 will actually turn into carbonic acid. All right, guys, so let's go and write that down. So H2O plus CO2 will yield in equilibrium because it can go backwards too via our carbonic anhydrase enzyme. So will yield carbonic, oops, sorry about that, 2 hydrogens here, carbonic acid. All right, so it's going to yield, I'm going to rewrite it again, sorry about that. It's going to yield carbonic acid. All right, but with the help of what enzyme, right? With the help of what enzyme is going to catalyze this step, right? It's going to be carbonic anhydrase. All right, so that's that. And now, once we have carbonic acid, we know that carbonic acid can then dissociate into bicarb and hydrogen cations. So what we're going to see is this. So now, let's go and draw it up here. So our, you know what, that's an equilibrium also. So we'll have to, you just draw another arrow going back, right? Let's go and draw that also. Let's say that, or you know what, let's just go and draw the actual equilibrium just to be accurate, right? Just going to go like that and like this, all right? So this will dissociate into a hydrogen cation, so a hydrogen cation and bicarb, right? So let's go and choose different color, bicarb, all right? So let's go and review that one more time. So CO2 can enter from the blood into the proximal convoluted tubule via the basolateral side, and CO2 and water can join, right, can react with each other, forming carbonic acid via carbonic anhydrase. Then carbonic acid in equilibrium can dissociate into hydrogen cations and our bicarb anion. Now our bicarb anion can then leave and go into the blood, all right? That way we have some neutralization reactions going, right? Because it can, if bicarb goes in the blood, it'll raise the pH just a little bit, right? So this is how we regulate pH, right? And CO2, once CO2 comes in, we can see that CO2 leads to hydrogen cation formation, which is what we see in an acidic solution, right? So we take in CO2, right? We produce hydrogen cations from that. So notice that we're actually getting a buildup of hydrogen cations inside our proximal convoluted tubule cell. All right, and then we actually let out bicarb back into the blood. All right, and the extra hydrogen cations that start to form can go back and participate in this channel, right? Our sodium hydrogen cation channel. All right, guys, so let's go and actually put this in here too. So a lot of our bicarb actually goes into blood this way via our kidneys. Okay, and so out here, since we have a lot of hydrogen cations, what can happen is, remember, we have a lot of bicarb that got filtered from the glomerulus into the Bowman's capsule and started going to the proximal convoluted tubule, right? Remember that from our previous videos? So if we draw a bicarb here, if we draw a, you know what, let's stay consistent with the colors, sorry about that. If we draw a, let me fix this real quick. If we draw a bicarb here that's already in the filtrate of our lumen of our proximal convoluted tubule, bicarb and hydrogen cation can actually react together and form carbonic acid. So then what we're going to see is that this right here and our bicarb, right, react together and can form carbonic acid, right? Carbonic acid. And so carbonic acid then needs carbonic anhydrase to dissociate into water and CO2, right? But it turns out that we actually have these cool membrane-bound proteins on our proximal convoluted tubule, cell, right? Specifically on the apical side, all right? So on the side of our lumen. So these right here are membrane-bound carbonic anhydrase enzymes. All right, so let's go and darken the H a little so we can see that, all right? And so what's going to happen is that these carbonic acid will then go and react with this and actually form, right, CO2 and water, all right? And so, and then water can actually go ahead and eventually, right, get reabsorbed and end up into the blood, right, like we talked about in our previous videos. So we have 65% of our water actually getting reabsorbed in our proximal convoluted tubule. All right, and so that's the mechanism that we have in our kidney that can regulate pH. Okay, so we reduce acidity, right, and then we take out some CO2 from the blood, right, and we see that from that we form hydrogen cations, and so we actually replace that, right, with bicarb to regulate the pH by maybe increasing the pH by a little bit if our blood pH needs to be regulated, right? So a lot of our bicarb in this way is reabsorbed back into the blood, all right, to regulate the pH. All right, so that's how we see pH regulation in our proximal convoluted tubule, and later on we can talk about other hormones that can actually straight up act, right, on the basolateral side that we'll see. For example, like parathyroid hormone will actually act here and prevent a channel on the apical side from reabsorbing hydrogen phosphate ions, all right? Because we'll see later that phosphate ions are actually good for rebuilding the bone, all right? And so when parathyroid hormone is present, we actually break down bone and increase calcium levels. So in that case, we wouldn't want phosphate ions to get reabsorbed into the blood because we don't want to build the bone. We want to break down the bone so we can increase calcium levels. So we'll see how parathyroid hormone, for example, right, among many other hormones, and how that hormone will actually affect the kidneys, right? The proximal convoluted tubule cells of the kidneys. And we'll see that in a future video. But for now, this is what I want to get through in this video. So I hope this video made sense to you guys. I hope to see you guys in my future videos. We'll talk about more cool topics about biochem, physics, and chem. Don't forget to hit that notification bell, like, and subscribe. See you guys later, and stay safe.